Hi everyone. Today we're going to be talking about the very most important group on the periodic table, the other nonmetals. So our goals today, we're going to learn the properties of the other nonmetals. We are actually going to finish our periodic table by shading in the other nonmetals and adding charges to the remaining columns in the A group. And we're going to learn just a tiny bit about what covalent bonds are. So before we go any farther, make sure that you have a note paper and pencil to take notes. Make sure that you've got your colored pencils and make sure that you have your periodic table handy and ready. So let's start with what elements we have here. So the other nonmetals includes hydrogen in column 1A, carbon, nitrogen, oxygen, phosphorus, sulfur, and selenium. I would like you to pause this video now, go ahead and pull out your colored pencil, shade in those elements, and make sure that you add them to your key under other nonmetals. So make sure you have them added to your key under other nonmetals. So pause this video and hit play when you are ready to continue. All right, ready? Let's move on. So, some things to know about these other nonmetals. They tend to have relatively low melting points. Many of them will actually be gases at room temperature, though not all of them. Sulfur and carbon can be solids at room temp, while nitrogen and oxygen and hydrogen will be gases. These things have a tendency to bond with themselves using a type of bond called covalent bonds. So for example, in nature, you're never going to run into a single nitrogen atom. Instead, you'll find something called nitrogen gas, which is two nitrogens bonded together. Likewise, you're pretty much never going to find a single lone oxygen in nature. Oxygen by itself isn't stable. It doesn't have 8 valence electrons. So it will actually covalently bond with a second oxygen atom to form O2, also known as oxygen gas. The same thing is true with hydrogen. A single hydrogen atom is not stable, but if you pair up two of them, they can covalently bond by sharing some electrons, and H2, hydrogen gas, is stable. This property of forming diatomic molecules, by the way, is actually shared with the halogens, which you'll notice are also nonmetals. Many of the halogens can form diatomic molecules. That means a molecule with two. That's what the prefix di means. Di means two. So diatomic molecule is a two-atom molecule, where those two atoms are just two of the same things paired up. And that's how you tend to find these things in nature. Now, the other nonmetals are capable of both ionic and covalent bonds, but they're not metals, so they cannot do metallic bonds. So let's start with column 5A, because you'll notice these things are kind of spread out across the different groups on the periodic table. I would like you to pull out your notes, and in your notes, I want you to draw a planetary model of the atom nitrogen, and right next to it, I would like you to draw a Lewis structure for nitrogen. Now, make sure you take a moment and look at those two. They should look pretty similar. You should see that the Lewis structure is like a planetary model, except you only draw the valence electrons and the element symbol. And once you have those two things, I want you to predict how many electrons nitrogen needs to either gain or lose to become stable. And when you do that, think, if this were to form an ion, what would the charge of that ion be? So go ahead and pause this video now while you draw the Lewis structure and planetary model of nitrogen, and hit play when you're ready to continue. Ready? All right. So let's think about nitrogen. Nitrogen is in the second row of the periodic table. That means I needed to draw 1, 2 electron shells. Nitrogen is element number 7. That means it has 7 protons. Now, nitrogen has a mass of 14, right? On the periodic table, it says 14.007. That's about 14. We know that that mass comes from protons and neutrons. So if we have 14 total and 7 of it came from protons, the other 7 must have come from neutrons. So we know that nitrogen has 7 neutrons. Now, that innermost shell can hold up to 2 electrons, so I went ahead and filled that innermost shell with 2 electrons. The second shell is going to be holding our valence electrons. Now, looking at nitrogen, it is in column 5A on the periodic table. That means it has 5 valence electrons. So when you place them, you should have put 1 in each quadrant first. So 1, 2, 3, 4. And once you had 1 valence electron in each quadrant, you could make a pair. So when you have nitrogen, either as a planetary model or as a Lewis structure, you should always see one pair of electrons. So here we've got two electrons that are paired together. That's a single pair. And we have 1, 2, 3 unpaired electrons. As we move through this, you're going to hear me talking about paired versus unpaired valence electrons a lot. That's because that idea of which electrons are in pairs and which ones are unpaired is going to be extremely important for understanding covalent bonds. Because every single one of those unpaired electrons is going to be capable of forming a bond with another atom. So nitrogen has 5 valence electrons. We've got 1 pair, 3 unpaired. If nitrogen wants to form an ion, it needs to pick up 3 more electrons. Basically, it needs to fill out each of these quadrants. Now, if it gains 3 electrons, it's adding 3 negative charges. So if you have 0 plus -3, well, that gives you -3. So you're going to end up with -3 as the charge for nitrogen ion. So a nitrogen ion has a charge of -3. Now, it's important to remember that everything in nitrogen's column is sort of in the same boat. If you're in column 5A, you have 5 valence electrons. That means if you're in nitrogen's column, you're going to need to gain 3 electrons. And if you gain 3 electrons, you're going to have 3 extra negative charges, so you'll have a charge of -3. So above column 5A, that's nitrogen's column on your periodic table, go ahead and fill in a -3. Let's move on to our next column. So let's take a moment and look at column 6A. This is oxygen's column, and you can see both oxygen and sulfur and selenium are in this column, along with some of the other elements we've already talked about. So in your notes, I want you to do the same thing. You're going to draw a planetary model for oxygen, and right next to it, draw a Lewis structure for oxygen. You should notice that the Lewis structure is just like the planetary model, except all you have to draw is the element symbol and the valence electrons. When you do this, I want you to pay special attention. Where do you have electrons in pairs, and where do you have electrons that are solo? I also want you to think, well, how many electrons would oxygen need to gain or lose to be an ion, and predict the charge of that oxygen ion for me. So go ahead and pause the video now and hit play when you're ready to continue. Are you ready? All right, so here we have oxygen in column 6A. So some things to note. Oxygen is element number 8. That means it will have 8 protons. Now the mass of oxygen is 15.999 on my periodic table. That's about 16. So if we have 16 mass total, 8 of that came from the protons. The rest of it must have come from the neutrons, so we have about 8 neutrons in most oxygen atoms. So an oxygen atom will have 8 protons and 8 neutrons. Now oxygen is in the second row of the periodic table. That means it has 1, 2 electron shells. Now we know that we fill that innermost shell first, and it can only hold 2 electrons, so we have 2 electrons in that innermost shell. And then we can move on to the next shell out. So for that next shell out, oxygen is in column, remember columns are vertical, column 6A. And for the A groups, the column that you're in tells you how many valence electrons you have. So oxygen in column 6A has 6 valence electrons. So when you're placing these, you should have put 1 in each quadrant first, so north, south, east, and west. Doesn't actually matter what order you do that in. And then once you've got 1 in each quadrant, you could make pairs. So with 6 valence electrons, we end up with 1, 2, 3, 4, and then we can make pairs, 5, 6 valence electrons total. So looking at oxygen, we end up with 2 pairs of electrons and 2 unpaired electrons. That means that oxygen is capable of forming 2 bonds. So oxygen can form 2 bonds. Think about a water molecule. In water, you've got H2O. It's really an oxygen bonded to a hydrogen on either side, so that oxygen has 2 bonds. It can form 2 bonds because it has 2 unpaired electrons. And we will go into this in much more detail when we talk about covalent bonding. Now, looking at oxygen with its 6 valence electrons, remember things want to have 8 or 0 to be stable. So oxygen needs 2 more electrons. Now, if it gains those 2 extra electrons, it's going to be adding 2 negative charges. So 0 plus negative 2 is negative 2. So oxygen ions will have a charge of -2. And that's true not just for oxygen, but for everything in column 6A. So above column 6A on your periodic table, go ahead and write -2. Now let's take a moment and look at column 4A. Column 4A has carbon and silicon and germanium, tin, lead, and flerovium. And I want you to draw a planetary model for carbon and a Lewis structure for carbon. And as you're doing this, I want you to think, what will carbon do? Is carbon going to gain electrons, or is it going to lose electrons? So look at what carbon is doing as you build this planetary model and Lewis structure. Pause the video now, take a picture, and hit play when you're ready to go on. All right, so here we have carbon. So carbon has 2 electron shells because it's in the second row of the periodic table. It is in column 4A, which means it's going to end up with 4 valence electrons. 1, 2, 3, 4. And again, you want to put 1 in each quadrant before you make any pairs. So when you look at carbon, you're going to have 4 unpaired electrons. Now, this might have presented you with a little bit of a conundrum. Think, if carbon has 4 valence electrons, is it easier to gain 4 to hit 8, or is it going to want to lose 4 to get to 0? And the answer is neither. Carbon is sort of stuck in the middle. It can't quite figure out what to do, so it doesn't do anything. Carbon actually isn't going to form ions. And that's true of most things in column 4A. You're just not going to see an ionic compound with carbon in it. It doesn't do that. So carbon doesn't form ions, just like the noble gases don't form ions because the noble gases were already stable. They didn't need to gain or lose any electrons. So neither carbon nor the noble gases will form ionic compounds. So above column 4A and also column 8A, you can write an N/A for not applicable, or you could write like doesn't form ions or nope, whatever you like to remind yourself that you are not going to get ions out of those 2 columns. So column 4A and column 8A, they don't form ions at all. Carbon, however, can form covalent bonds. Now, covalent bonds are bonds that involve sharing electrons, and every single one of these unpaired electrons is capable of forming a bond. Now, we'll go into more detail about how this works tomorrow, but for now, the important thing to notice about carbon is that it has a lot of unpaired electrons. That means carbon can form a lot of bonds. Carbon actually is really, really awesome at forming big, complicated molecules, and that's something that makes covalent bonds really special. So at this point, your periodic table should be complete. I want you to take a moment and make sure you have all of the following features. So every single group should be colored. You should have the alkali metals, the alkaline earth metals, the transition metals, the lanthanides, the actinides. You should have your post-transition metals, your metalloids, your other nonmetals, your halogens, and your noble gases all colored in. You should have charges on the A group, so column 1A forms 1 valence electron, 2A forms 2 valence electrons, 3A has 3 valence electrons, and a charge of +3. Column 5A has 5 valence electrons and a charge of -3. Column 6A has 6 valence electrons and a charge of -2. Column 7A can form 7 valence electrons and has a charge of -1. And column 8A and 4A do not form ions, so they don't have a charge. At the very bottom, you should have a key for each of the groups that you can identify each of these groups. That should be separated into the metals and the nonmetals. And of course, metalloids are sort of neither. They're in between being a metal and a nonmetal. At the top, you should have a key for what is in an element box, including the atomic number, the element symbol, the element name, and the atomic mass. And you should have the formulas for how you figure out the number of protons, neutrons, electrons, the charge, and the number of shells for any atom. And at this point, your periodic table should be complete. If you're missing any of those things, pause now, complete the periodic table, and hit play when you are ready to continue. So, I've mentioned covalent bonds a lot. That's because these other nonmetals are amazing at forming covalent bonds. If you want to see something that is made out of these elements, just look at yourself, because you as a living thing are primarily made up of those tiny handful of elements. You're 70% water, that's just oxygen and hydrogen. Any sort of carbohydrates that you have, carbon, hydrogen, and oxygen. All of the fat in your layers of skin, that's carbon, hydrogen, and oxygen. The proteins that make up your fingernails, your hair, all of that is carbon, hydrogen, oxygen, and nitrogen. The DNA that has all the instructions for how to make a human being, that's carbon, hydrogen, oxygen, nitrogen, and a little bit of phosphorus. Those handful of elements are what living things are made of. Not just human beings, but plants, animals, funguses, bacteria, viruses. Everything is made up of that handful of elements. And this is possible because covalent bonds are capable of making massive, complicated, interesting molecules. This is the part where chemistry starts getting really fun because you can actually build exciting things out of these. So that handful of elements are the elements of life. And we're going to talk about covalent bonding in our next lesson. So as we prepare for covalent bonding, I want you to think about Lewis structures and planetary models and how a Lewis structure is like a planetary model. And every time you draw a Lewis structure, I want you to notice the paired versus unpaired electrons. Because when you start looking at those Lewis structures, every single one of those unpaired electrons is capable of forming a bond. And that's going to be how we build these big, complicated molecules.